First bad version. This one sneaks up on candidates. First bad version looks easy, but it tests whether you can turn a plain binary search into a boundary finder. FANG interviewers love it because getting the loop and the off by one details right under pressure is a real signal. Let's lock it in with basic, so your explanation and code are crisp and bulletproof. Solution walkthrough. Breakdown. We have versions 1 through n, and an API called isBad of X that returns true if version X is bad. Once a version is bad, every later version is bad. We must return the first bad version's index. That's a classic monotonic pattern. FFF, FTTT, T. We're not searching for a value, we're finding the leftmost true. Assess. Linear scan is O of n, but the predicate is monotonic, so binary search gives us O of log n time and O of 1 space. The pitfalls are the termination condition and deciding which side to keep when mid is bad. If mid is bad, the first bad could be mid or somewhere to its left. If mid is good, the first bad must be to the right. Structure. We keep a closed interval from left to right, initialized to 1 and n. While left is less than right, we compute mid. If isBad version of mid is true, we shrink right by setting right equal to mid. Otherwise, we move left past mid by setting left equal to mid plus 1. When the loop ends, left equals right, and that index is the first bad version.
Let's try to implement it using solution 1. We begin by defining a solution class that extends version control. That gives us access to the isBad API, which checks whether a given version is bad. Then we declare the first bad version method, which receives n. N is the total number of versions we may need to inspect. Next, we initialize 3 variables. L starts at version 1, R starts at version n, and bad starts as n, meaning the latest possible bad version in the worst case. We will update bad whenever we discover a bad version earlier than our current best guess. After that, we start a binary search loop. We continue as long as the left boundary has not passed the right boundary. Because each step cuts the search space in half, this runs in O of log n. Inside the loop, we compute the midpoint m using a safer formula. We take L, plus the difference between R and L, divided by 2. This avoids overflow and gives us the next version to check. Next, we call isBad version on m. If version m is bad, that means the first bad version could be m, or something earlier. So we update bad to m. This makes m our best candidate so far, and then we move the right boundary to m-1. That way we keep searching the earlier versions to see if there is an even earlier bad version. Otherwise, if version m is not bad, then the first bad version must be after m. So we move the left boundary to m+1. This continues until the loop ends. By then, we have narrowed down exactly where the earliest bad version must be. And finally, we return bad. At this point, bad holds the first version that turned bad. And that's how this algorithm works. It sets up a search range from version 1 through n. Then it uses binary search to check midpoints and shrink the range toward the earliest failing version. It keeps updating the best answer along the way. Efficient, simple, and elegant. Check. This test evaluates the first bad version algorithm, which uses a binary search approach to find the earliest version that fails. N equals 5. And the first bad version is 4. That means versions are labeled from 1 through 5. Version 4 is the first bad version, and any version after 4 is also bad. The goal is to find the smallest version number that is bad. Here is how the logic proceeds. First, check the middle of versions 1 to 5. That midpoint is version 3. Since version 3 is good, the first bad version must be later. Now we search the range from version 4 to version 5. The midpoint is version 4. Since version 4 is bad, it becomes our current best candidate. Then we check the left side to ensure there is no earlier bad version. Everything before 4 is confirmed good, so the first bad version is 4. The output is 4, matching the expected 4. This confirms the solution correctly identifies the earliest failing version. Now let's try another implement approach using solution 2. We begin by defining the solution class, which extends version control. That lets us call the provided isBad version API. Then we declare the first bad version method, which receives n. N is the total number of versions. Next, instead of searching directly inside this method, we hand the work over to a recursive helper function. We start with the full search range, from version 1 to version n. Now we enter the recursive helper. It takes the left boundary, L, and the right boundary, R for the current search window. Here is the base case. When the left boundary meets the right boundary, we have narrowed the search down to a single version, and that version must be the first bad one. So we return L. Next, we compute the midpoint M, using the overflow safe formula. We take L, plus the difference between R and L, divided by 2. This midpoint helps us decide which half still contains the first bad version. If version M is bad, then the first bad version could be M, or something earlier. So we recursively search the left half, from L to M. Otherwise, if version M is good, the earliest bad version must be after M. So we recursively search the right half, from M plus 1 to R. And that's how this algorithm works. It passes the full range into a recursive helper, then it cuts the range in half at each step, based on whether the midpoint is good or bad. It keeps narrowing until only the earliest failing version remains. Efficient, simple, and elegant. Check. This is the simplest possible scenario for the first bad version problem. N equals 1, and the first bad version is 1. There is only one version, and that version is bad. With no earlier versions to compare, it must be the first bad version by definition. No real binary search steps are needed, because there is only a single entry to return. So the correct result is 1. The output is 1, matching the expected one. This confirms the solution correctly handles the minimal case where the first and only version is already bad.
Let's have a quick recap. Breakdown recap. So, wrapping it up, the first bad version problem isn't about finding a value, but identifying a boundary. We're given versions from 1 to n, and once one version is bad, all the ones after it are bad too. Our goal is to pinpoint the very first bad version, the exact point where good turns into bad. Assess recap. We compared our options and saw that a linear scan would work, but it's way too slow. The key insight is that this setup is monotonic, which means we can apply binary search. The trick is in how we move our pointers, deciding which half to keep and which to drop, while never losing sight of the possible boundary. Structure recap. The plan was simple but precise. Start with a full range from 1 to n. On each step, check the middle version. If it's bad, the first bad could still be to the left, so we keep mid in play. If it's good, we move right past mid. The loop ends when both pointers meet, and that meeting point is the answer. Implement recap. In the implementation, we used a clean binary search loop, updating our boundaries carefully. We avoided off-by-1 errors by keeping the logic tight. Bad means shrink the right boundary, good means move the left boundary forward. It's a perfect example of control and precision in algorithm design. Check recap. When we ran the tests, every case passed, whether the first bad version was early, late, or right at the start. The function consistently returned the correct index with O of log n time and O of 1 space, just as expected. The big takeaway? Boundary-style binary search is about discipline, not just finding something, but knowing exactly where a condition changes. Mastering this pattern builds the confidence and accuracy that top interviews are designed to test.